Welcome to the Deep Learning 101 series, your beginner-friendly guide to understanding how machines actually learn. In today's video, we are diving into the fundamentals of neural networks and unlocking the mystery behind forward propagation. Whether you are a brand new to deep learning topic or brushing up your skills, you are in the right place. Let's get started. First, you need to set baseline here. If you are ever wondered how a neural network thinks and makes predictions, it all starts with forward propagation, the heartbeat of deep learning models. And we will break down deep learning fundamental concepts and neural network, especially highlighting the practical use cases. Deep learning, as a definition, is a short term of deep neural networks, which is a subset of machine learning and has the main purpose from data, but not just tabular data. It also learns from videos, images, text, as we will see during this series. One of the main DL or deep learning characteristics is the deep learning architecture. It automates data with many hidden layers, whether it's a tabular data or with a complex dimensions or unstructured data like images, videos, audio, and text or hashtags. Deep learning is a powerful tool because it's capable of capturing complex nonlinear relationships, especially when we are concerned of curse dimensionality or imbalanced data, or even data is incorrectly labeled. If you are familiar with machine learning techniques and in simple models, you might like this intuition. You can see on the right side of this slide, we have three circles: machine learning, deep learning, artificial intelligence, and we see that they all intersect in some areas, and that we will define later in this series. From basic models to advanced and more complex models, we are shifting from basic models such as classical machine learning, logistic regression, naive Bayes, KNN. Then we have intermediate level, such as in simple learning, random forest, KG-post, YGBM, CAT-post. Moving on to more complex models, we see it in neural networks and deep learning, such as CNN. And finally, the advanced level with the reinforcement learning, we see it in Q-learning, when the data is semi-labeled. Deep learning is used to solve practical tasks in a variety of fields, such as computer vision, aka images, natural language processing, aka text information, and automatic speech recognition, aka audio and videos as well. Moving on to deep learning libraries in Python, we see PyTorch, TensorFlow, TensorBoard, and FastAI. So PyTorch is developed by Facebook and for its dynamical computational graph and used for deep learning tasks. And these are the most common functions used in PyTorch. Then we have TensorFlow, that it has also Keras, the second most common library that handles deep learning tasks. TensorFlow is developed by Google and used for complex deep learning models, high computations level API. Usually it's preferable to start with PyTorch, then move to TensorFlow. And of course, these are the most common functions used in TensorFlow. Then we have TensorBoard to visualize the model performance by tuning the hyperparameters and optimizing the model, tracking model behavior. Then we have FastAI. FastAI is a high-level deep learning library built on top of PyTorch, designed to train neural networks easier and more accessible, with fewer lines of code. One advantage is its practical focus, making deep learning approachable for both beginners and experts. I will add all the sources in the video description. Then we have the deep learning lifecycle. I feel you might remember this from my previous video, machine learning pipelines, but this one is a bit enhanced and compatible with deep learning lifecycle. Define the business questions. What are we trying to solve here? Then we have the importing libraries, pandas, sklearn, TensorFlow, PyTorch. Then we have the dataset importing, and Then we have data understanding and data wrangling, feature engineering, and data labeling. We train the deep learning model on unstructured data. These are the steps that happens before training our model. Next, we have the train validation test split. Then we have the model training on neural networks model. Then we have the cross-validation, then model evaluation and hyperparameter tuning, feature importance, model stacking. After having good individual models, the for loop to achieve that. And yeah, by the way, regarding the feature importance, we also use for feature importance techniques such as SHAP or LIME. And finally, the last section of the deep learning lifecycle is training the best model and find the model evaluation and applying the best model on the test data, then deploy and monitor and the feedback loop. Next, we have the deep learning practical use cases. So basically, there are most use cases relevant in 2025. First, we have some US markets deploy in-store cameras with deep learning models, face recognition, to analyze customer facial expressions and emotions. This helps in product placement and engagement. On the other hand, it breaches the data and users' privacy. And that's why it is strictly prevented in Europe due to GDPR. GDPR stands for General Data Protection Regulation. Another practical example is streaming platforms use deep learning models as in natural language processing and audio pre-processing to censor vulgar or explicit language in songs. Systems automatically provide playlists like clean, explicit playlists. Next, another practical use case in deep learning is censored content on social media to identify and prevent specific topic, discriminatory, hateful content in images, videos, or even in text and hashtags based on deep learning or using deep learning models. And finally, the most significant practical use case enhanced by deep learning is in medical areas, cancer diagnosis and detection, especially using CNN model, the model from doctors and experts. However, in the recent years, we witnessed a new specialty where doctors are actively learning coding, computer vision, and neural networks to design better diagnostic tools and understand and validate the new models' results in clinical settings. We have the deep learning models' most common types. The first one is the most straightforward technique, which is multi-layer perceptron, MLP. It's a classical feed-forward neural network and used with tabular data on classification and regression problems, as well as basic image classification, and I will touch on MLP technique later in a separate video. Then we have CNN. So basically, one of the most common techniques in deep learning that focused on pattern recognition, image and video classification, and object detection. CNNs are grounded in linear algebra and matrix multiplication. Typically, CNNs consist of three main layers: convolutional layer, pooling layer, and fully connected layer. So that doesn't mean every model has only these three layers. Modern CNN, like ResNet, can stack thousands of layers with advanced techniques such as skip connections, patch normalization, and depth separable convolutions. Challenges related to CNN are computational costs and processing units, GPUs, graphical processing units, as well as model complexity. It also, another big challenge is the domain expertise, which is pretty critical, with solid knowledge in testing configurations, hyperparameter tuning, and optimizers. Deep learning isn't magic, it demands deep understanding. Deep learning techniques are powerful, but still, without grasping the math, the layers, and the parameters, your model might collapse. Or you can spend weeks in a loop for tweaks and fixes, only to find yourself in unbreakable loop. It's not just about stacking layers, it's about knowing why they are there. Then we have the RNN, typically used in natural language processing and speech recognition applications, as Siri and Google Translate. Its advantage is it uses sequential or time series data, making the RNNs ideal for tasks where order and context matter. RNN use feedback loop to optimize model predictions. It also adjusts weights via backpropagation through time, and the gradient descent, which minimize the loss function. Don't worry if you don't have any knowledge regarding these two techniques, I will cover them in the next video. Challenges around RNN are vanishing gradients. That happens when the weight parameters approach zero. That reflects that the algorithm is no longer learning. Another thing is exploding gradients that occur when the weight is too large, creating unstable model. And to overcome this issue, we can reduce the number of hidden layers within the neural network. RNN are efficient with relative medium-sized datasets due to the long training time of the model. RNN bring memory to deep learning. Their ability to capture sequence and context has powerful innovations in natural language processing and speech. But without careful design, they can break, either forgetting too quickly or exploding out of control. So understanding these behaviors is key to building efficient RNN-based models. Moving on to another technique, neural networks core concept. So basically, we have information plus knowledge equal prediction. I want to highlight how neural network works. It accepts data inputs as information and weights variables as knowledge to output predictions. Or if we enhance this definition, I would say it takes information, the dataset variables, it applies the knowledge, aka the learned weights from training, then it gives you the prediction, the model's output. Cool? And the simplest neural network equation is input multiplied weight is equal prediction. Remember this equation because it's very critical and we will come to this one later. Then we have the NNN, or neural networks learning definition. So basically, it's a series of algorithms designed to recognize patterns and relationships in data through a process that mimics the way the human brain operates. And I like this definition. I find it on DataCamp. What are the neural networks? Feel free to check it out. I will add all these sources in the video description. How neural networks make prediction? The NNN model prediction. Again, the first and simplest equation is input multiplied in weight gives us our prediction. This is, we'll mark it as equation 1. Then, how can we say if our NN model make a good prediction or not? Simply, we need a baseline. If the model accuracy score is equal to the baseline score, then our predictions are great. If not, then we need to work more on the model. Simply, we can define that as delta is the neural network model prediction minus baseline, the good predictions. Initial baseline of neural network is set at 80%. Let's assume if we have our model neural network gives us 70% accuracy, then the delta is minus 10%. Okay, and we will come to this one later. So we can say that the baseline is 80%, and since delta can have positive value or negative value, it's safer to stick with the error of the neural network model instead of the delta. And error is calculated as this equation, equation number 3, the neural network model prediction minus baseline, the good prediction, power to 2. So now the error is 1%. Remember, delta is important to tell us the amount of difference between the neural network prediction and baseline. Also, it defines the direction. So it tells us the direction and the rate of a change. And we will cover this one in detail in our next video when we talk about gradient descent. But let's stick with the fundamental advantage of deep learning over traditional machine learning, that it allows to directly modify model parameters and shape the logic behind predictions. However, this power requires expertise because there is a higher risk of training models on unrealistic or misleading patterns in the data, not related to the business problems or even the user's needs. Before moving to our next slide, just need to emphasize that weights determine how much influence each input variable or features has on the model's prediction. You can think of a weight as a measure of feature importance. Which variables in the dataset should we pay attention to and which to ignore? And as a beginning of training, weights are typically initialized at 0.5. This value is modified later to minimize the loss function, ideally bringing the loss function as close to zero as possible. The lower the loss function is, the more accurate our model predictions. Bring us to the weight and error relationship, which is critical and fundamental because the rest of the variables are constant and unchangeable. Back to equation 3. The model prediction has the input multiplied by weight, as we mentioned earlier. So the error can be calculated as follows: input multiplied by weight minus the baseline to the power of 2. And as you can see here, we can't change the input or the data variables. We can't also change the good prediction, the baseline, 0.8, but we can modify weight to minimize the error, aka the loss function. So how changing one variable can change the other? If we want to optimize the neural network model, the one variable we can work on is weight. This is the core idea of neural network, and later when we implement the neural network model using PyTorch or sklearn in the technique MLB or even TensorFlow, it's expected that you have solid understanding regarding the relationship between the error and weight. So you can build your own functions and for loops, defining the model parameters and boundaries correctly. So pause and read these lines one more time. Our last idea, the neural network forward propagation. It's simply input to layers to predictions. Of course, weights are tuned after many iterations, and the neural network model is trained multiple times to obtain the most optimal predictions of neural network. As you can see here, xi1, xi2 to the end reflect the inputs, and then we have the weights, and then we have the hidden layers, and then weights, and finally y hat gives us the predictions. Okay, so moving to forward propagation types, we have many inputs multiply with many weights as one prediction. Think of it as if we have salary prediction dataset, many features or the inputs will be education, marital status, age, company name, location. All these variables are contributing to predict the salary. Okay, and the weight, the initial weight is 0.5, but we will modify it later when we train our neural network model. Another type is many inputs multiply with many weights to give us many predictions, and this is the most common type. We will see later when we talk more about MLP method. And that's it for today. Thank you so much for watching. If you find my content useful, don't forget to like and subscribe, and I see you in the next video. Bye.